Okay. Hi, everybody. We continue our work. We shall continue analyzing how to use the Play library for regression tasks. This is the fourth lecture we are using Play to analyze the regression process in machine learning. In this lecture, we shall use the kernelRidge.vi. Remember, we have already worked with the ridge algorithm in Python. And we made some analysis and comparison between the ridge and Lazo algorithms with examples there. Today we shall try to realize this regression process by using Play in the environment of LabVIEW. Where this kernel exists, right-click on the block diagram as usual, go to DF to Play, then go to Machine Learning, Supervised Machine Learning, then to Regression. Within Regression, you will find here this palette, this VI, which is the kernel of Ridge, kernelRidge.vi. If you don't know anything about it and you want to know something, just right-click it and go to the help. It will show you the original information in sklearn and give you the syntax of this algorithm and the parameters which could be moved to the algorithm with the default values for each. So remember, we have said to you once that instead of using lambda, the coefficient in Ridge is called alpha, and it has a value here, default value equal to 1. The kernel is linear as default, and the degree is given 3, and coefficient 0 equal 1. With some information about the kernel. We know about that. You remember, we have mentioned that this ridge itself has or is called or has a regularization abbreviation or name called L2 normalization. Kernel ridge regression combines ridge regression with L2 normalization. And L1 is for Lazo. You remember that, and we have an idea about it. Downwards, you can see some explanations for the parameters which you pass to the algorithm, like what is the kernel or the alpha coefficient, how much it is, the gamma coefficient. An example, degree, for example, it is a float value. The default value is 3. It is the degree of polynomial kernel ignored by other kernels. So it is usually functional only for the polynomial kernel. the polynomial kernel exists within the ridge. I'll show you just now. Yes, and so on. So the dual coefficients, for example, I shall talk about it just now, representation of weight vectors in kernel space, and so on. We will not go through it in detail here. It is not time for that. So you know the way how to find information about the ridge or kernel ridge. In this example, we are also using the Boston house dataset. To simplify the things, I did not use the dataset and did not divide it to two parts, X and Y. I have taken the result of our work in the previous example, in the previous lecture, and here this array, really it was there as an indicator which represented the values which we have read as CSV file in the previous example. And this is also the two-dimensional array which represents the Y values, the target values, and also it was read from a CSV file. Of course, the values, the good thing here in LabVIEW that if you copy and paste the indicator here, you can change it directly to be a control. Now it is a control, and the data from this control now is fed to the split data VI here. So this is the, as you see, the Y value, and this is the X data sets. Of course, they exist as numbers. If I double click it here, you will see it. Here it is the, let me enlarge the front. Yes, this is the X values. As you remember, there are 13 features, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There should be 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there are 13 columns as shown here. This is the size of the array, and 506 samples or values. The target is also 506 rows with one column, as you see here, and you can see it here. I did not show all the values here. Also, I didn't show here 506, but just to be sure that we are working with the same data set which we have worked with in the previous lecture. So these two arrays now are fed to the split data VI, and now we have the training set and we have the test sets as we did in the previous lecture. And through the node here, the property node, we set, here is the set parameters, we set the values to the kernel, to the algorithm. This is just for initialization, the algorithm. And after that, we fit the data. We fit the function to the data, and as a result of that, we can predict the output array or output values and find the score. This is all has been done in the previous lecture. What new here is I have put here a get attribute VI. How to find it? As I told you, just put the cursor on the router and now go to kernelRidge palette. You will find here a number of palettes which are associated with this kernel. So you can take the VI which you are interested with. I am interested with get attributes, so I put it there, get attribute VI, and from this attribute VI, I supply the router to the property node here. Here, this is also another property node. And from here, we have the attributes. The output will be the attributes. How I can know that? You just put the arrow here, click it, and now you will have all the options which are associated with this node. Oh, I selected read, write attributes. So it is selected now, it is here, read, write attributes. Also, I have selected names where it is names here. There should be here read write name, for example. I have taken it just to show you. Now this is the output, the indicator which gives you the name which is associated with it. And here you have, as you see, this cluster which shows you the attributes. If I double click it here, you will see it on the front panel here. This is the attributes, which is, as you see, an array. Let me show you from the beginning. As you see, this is two-dimensional array with one row only, and the size of this array must be equal to the number of the samples or the rows in the training set. So if I go back here, I have taken this cluster and unbundled the cluster by name. Here we have the dual coefficients of it, which I need. I can see them again. And now I have the size of the array. I wanted to be sure that the size is equal to the number of training values, training samples. So now, if you double click size 3 here, you will find that it is really 405 values, and we have only one row. This is the row, and these are the columns. These are columns, and this is one row. So, as you see, we have 405 because the original total X values were 506. We took 101 for the testing, and we have left 405 for the training. So exactly we have as shown here. So what can I say about it really? Really the dual coefficients here represent the array, as you have seen, with a number of columns equal the number of the rows, and one row here, and the number of the rows in the original data set, of course. Yes, and this is practically represents the values which you have seen up in the front panel. These values which represent the weight for each sample in performing the prediction. It is really just to know something about what is inside and how the algorithm works. But concerning the outputs or inputs of interest, they are done internally, and we do not need to know about it, or we are not going to use it. I am just showing you how they exist and what they are, not more. Okay, so now at the end, of course, we have taken the predicted values with the testing values of y and have already plotted the original data set with the predicted values. I have plotted them twice so that I can show you at the same time if one of them will be shown as scatter plot and the other will be shown as you see curve. Okay, now what the result let us run it. Here the previous result which I have here 0.67. Remember, we have got in the previous example for the Boston housing dataset such a number. It was practically the 0.66 and so on. It is the same. Anyhow, now let me run it in front of you and see what we shall have. Now I am running the program. It has finished. It is now 0.7. It is the same. Let me run it another time. 0.66. It is the same practically. Another time. So as you see, the deviation of the score is very limited, and this means that the predicted coefficients, these coefficients are having a practically constant values, and there is no serious biasing there. Okay, now let us all, if we consider, of course, the parameters of the regressor here, as you see here, read-write parameters. I want to read the parameters which are associated with our regressor. So it is in the linear mode, and the degree here is given 3. And as I told you, it doesn't matter that much, because it is very useful when we work with polynomial regressor. Here we have polynomial regressor. It is 3. Now, if we look and try to manipulate or to work with another selections here other than the linear, let us try with the nonlinear RBF, for example. Remember, in the previous lecture, we have found that for this dataset, the linear regressor has better results. Now, if I run it again, it is minus, the score is minus 5.9. It is in minus, so this means that this is a bad result. And as you see, really, there is big distances between the real values and the predicted values of the data set. So this nonlinear regressor is not adequate for this data set. Let us try, for example, the cosine, for example, option. And now let us run the program. It is working. Now it has a score 0.3. It is normal, but it is not good. And this is seen here, of course, if you compare between the red dots and the values predicted here, you will find that there is some difference. The difference is not small, and this is shown through the score value here. And also we can feel it when you compare the values here between the y-test and the y-predict. Here it is 25, here it is 34, here 22, here it is 16. They are far away from each other. Of course, you can also modify the results here and try to make it better, but let us try. For example, what we can manage here, the alpha, the coefficient alpha is a float here, and it is 0.2. Let us try to make it 1.02, for example, to increase it. Remember, by increasing the coefficient alpha, we are shrinking more the coefficients, and the work should be a little bit better. Now it is 0.3, and you see that really it is much better than before. Let us try to make the alpha 2.2, for example, and now run it. No, it doesn't improve. It is practically the same level. So we are limited here for this data set. The coefficient here, as suggested, as a default value is 1. If I increase it by 2 numbers, maybe it affects the results, yes, but in the bad direction. So maybe I put it 0 and try it here now. It is also about 0.2. So we can come to a conclusion that working with the cosine is normal, but it is not the best choice. Let us go back and try again with the linear kernel, or let us try with a polynomial, for example, and see how it works. This is the polynomial. The degree is given 3, which is as default value. Alpha here, let us be small, 1.2, and now we run it and see. But it is not a good work here. Minus. Let us try to improve or to increase the level of the power of the polynomial. Run it. It is worst. So it doesn't fit with this data. Again, maybe we try the last time for the poly, and now we run it. Bad. So as a result of our analysis, we come to a conclusion that the best choice for us is to work with the linear, and we came to this result in the previous lecture. And now if we run it, as we shall see, it will come back about to 0.7 or like that. 0.6, we can improve it a little bit. Here, the alpha float, let us increase it a little bit. Now, 0.67. Okay, so as you see here, the distribution also of the data set, the original one with the predicted ones, really is very close to each other, and also it is shown in the graph here. Okay, so I think it is enough with this example. Let us move to another example. In this lecture. Okay, we open, okay, it is opened. So let us go to open, and we open another example. I have prepared for you another 2 examples. One of them is this one. But as you see, we use here also the same regressor, the ridge regressor. We are working today with the ridge regressor. What is the data set we are working with here? The data set which we are working with here is the same data set which we used when we analyzed the ridge regressor in Python. So there is a file, 2 files, where I saved the training or the X values, and another one where I saved the Y or target values. These values now are read by using this function here, read delimited spreadsheet VI, and at the output I get 2 arrays, one of them for the X values, here it is, and the other one will be for the Y values. This here is the Y values. Now we go back. So we have the X values fed to the split data VI, and the Y values fed to it. I have also shown you here the size of both of them. This is 500 samples with 4 columns in this data set. This is not the Boston housing data set. This is a synthetic data set. We have realized it ourselves. We have built it or constructed it ourselves. And the other one also, the other part, which represents the Y, is having a size here, which is also 500 samples, but with 1 column. Okay, now if you look at the curves here, this is the fitting curve, which results for this data set by using this ridge algorithm. The score which we have here is about, as you see, 0.03. It is very low. It is very near to 0, which means that this is not a good result. And the mean square error is 2.7. This is acceptable value. It is close to 0 value, but not that good also. And the score here is also normal, but it is very low. So why this happens? This is because the data set which we have in the Python example has given us the same results as we did here, as we have here. And this is for many reasons, but not because of the algorithm. We are using the algorithm or the ridge algorithm here as we did that before. Let me show you and remind you again with it quickly. So if I go back to LabVIEW, sorry, to Python, okay, now I open my notebook and go to the Python folder. Now, this is my folder where the program of Python exists. It is exactly the same data set which we are using now with LabVIEW, with Play LabVIEW. Okay, it is opening now. If I go downwards, it is very close. Okay, it is now here it is. This is our data set. As you see, it is a synthetic data set, as I told you. This is the expression of X. It has 500 points. As I told you, we have 500 samples. And this is the Y. As you see, it contains a nonlinear component because of the sine function and with an added noise here. And also we have 500 samples at the same time. And this is the added noise. If you look at the results which we have received, again, you will find really we have the same data set, and this is the curve which represents the predicted curve or the regression curve. If you want to see the values, the estimation of the quality of the regression, you will find R squared score is 0.06. In play, we have it 0.05, practically the same. And the mean error value, mean square error value is here 2.64. There it is, I don't know, now I'll show you. It is there also about it. It is about 2.73. Here 2.39. Practically the same. We have the same results and the same curve and the same character as we have already done by using Python. This is a clear evidence that this library works very fine and gives accurate results as we have with Python. Here is an additional work I have done. I have just estimated the MSE for you so that I can compare it with the mean square error, which we have already achieved in Python. Okay, let us move and see another example where we use the same data set but with increased number of samples. So we have changed the data set. Let us go there. Now I shall go here and open another example for you where we use the regressor also. So this is the kernelRidge regressor, as we did before. This is the data set which we have now. It is in its character very close to the previous one, but it has a high number of samples. If we go to the front panel here and see the size of the features, 10,000 samples and 4 features we have only. And here we have 10,000 rows and 1 feature. This is the target. And as you see, now this is really because we have a sign component in the expression. You have seen in the previous example that it has a nonlinear character because of the sign component. So here, advisably to select the RBF. When I have selected the RBF and run the program, I have got a score equal to 0.85, a very high and very interesting result. It is about 1, which means that the work is done very nicely. And you see here, really, this is the regression curve shown here or shown here. Different. Of course, I can change it to line here to be as it is there. It depends how you like it. It is the same. But here as points, and there, as you see, because the points are too much, 10,000 values, they are shown as if they are a line on each other here, located on each other, as you see, but here they are shown as a line and not as dots. So now again, concerning the block diagram, I didn't change anything in the program. I have kept it as it was before. Just I have changed the number of points, and because of course the function is a sine wave and nonlinear, and we added a component of nonlinearity of noise there. So of course we have got this distribution of the data, and we have got this output here. If we go again and try to analyze what we may have, suppose we want to get to work with a linear regressor. Shall we get a good result? Here it is now a linear mode. Of course, if I run the program now, I shall have another picture. Let us wait a little bit. It takes time because the data set is very large. Yes, this is the regression line, as you see here, but really it is distance between any point here on the line and the other hundreds of points which are there is very large. So you can imagine that there will be a low score. If you look at the score here, it is about 0. It is positive, normal, but it is about 0 here, which means that this is not a good idea. Let us try maybe another to work with. For example, here it is a sigmoid. Let us try the cosine, for example, because this is a nonlinear character. The cosine may be closer to it. And if we run the cosine, I think it will be much better than the linear. It takes some time, as you see. Oh, yes, it is. It is trying to cope with the original one, but of course, it is not that good. The result is 0.12. Of course, we can, for example, I'm not sure that it will work, but if we increase no, the gamma must not be that high. It should be about 1 or 2. Let me try with another gamma. It is 1, 3, not too much, not much better. Practically the same result. Okay, so as you see, of course, at the output, I have got the dual coefficients again to show you how they are, but as I told you, they don't give any, we do not need it usually when working with the regressor, but they are existing, and I didn't try to extract for you the size and the number of points and related information for it because it is not required. Okay, so I think with this, we finish this analysis. We have looked carefully at 5 examples through 4 lectures. And I think with this, it is sufficient to work with play in regression, only in regression. We shall come back to play to work with it when working with logistic regression. But I want also to show you the other LabVIEW software, which is the analytics and machine learning toolkit through an example so that you can compare between both and make your choice. This will be done in the coming lecture. For now, it is sufficient. Wishing you the best. Have a good day and goodbye. Yeah.